With the understanding of Hurwitz's criteria and positive real functions, what we are now going to understand is synthesis of three networks. We are going to synthesize RC network, we are going to synthesize RL network, and we are going to synthesize LC network. So three different combinations of the elements are done, and we are going to synthesize RC, RL, and LC network with the given system function. So let us understand the properties of these RC, RL and LC functions. So if the given function, whatever equation which is given to us, which is the ratio of P by S by Q of S, this particular function which is either given in the form of impedance driving function or admittance driving function. So the functions will be given in what form? Either in the form of Z of S or y of s. So we will be given the system functions in the form of driving point functions. So what we have are driving point functions in the form of either z of s, impedance driving functions, or admittance driving functions y of s. With z of s or y of s, which is in the form of some p by s and q by s form, if such is the input, we have to identify whether it is an RC function, whether it belongs to an RL function, or it belongs to a LC function, right? The very first thing when it starts with synthesis is to identify what are the elements that are described by the given function, right? So let us start with RC function. So if we have a z of s which is defined with this, now here to understand RC function better, we have started with an example. So we have been given an example, and this example is the driving point impedance of a RC function. So we know that this is a RC function driving point impedance. Why do we call it as a driving point impedance of an RC function, or what are the characteristics of the RC driving point functions, driving point impedance function is, let us identify. So for that we have started with an example. From this we will identify the poles and zeros. So we now know how do we identify the poles? Equate the denominator to 0. So when we equate the denominator to 0, we get the values as S of 0, S as 0 and S as minus 2. So these are the two values which are the poles of the given system. How do we identify the zeros? To identify the 0, equate the numerator to 0. So when we equate the numerator to 0, we get the value of S to be minus 1 and minus 4. Right? So once we have been given with the system function, what is the very first step we need to do is to identify the poles and zeros. Now let us plot the poles and zeros. So after plotting the poles and zero, this is the pole 0 plot we get. This is the S-plane. So S-plane, the real part of the S-plane is sigma, the imaginary part of the S-plane is j omega. So the poles 0 and minus 2 are located here. This is the first pole. The poles are identified or labeled with a cross symbol. Zeros are labeled with a 0 symbol. So where are the poles? 0 and minus 2. So you could see here. This is your first pole. This is your second pole. So these are the two poles. Where are the zeros? Zeros is at minus 1 and 0 is at minus 4. So these are two zeros. So we have plotted the poles and zeros of the given RC function. Now with this we will identify the properties. Right? With this in front of us, let us identify all the properties that belong to a RC function. So look at the pole 0 plot and understand the properties. Then that gives a clearer meaning to us. So what does the RC function consist of? The RC function should have poles and zeros which are simple. You could see here the poles and zeros are not complex. They are all lying on the real axis, and that's why they are simple. They are not having any complex term. There are no multiple poles and zeros. So you could see there at one particular location there is only one pole. There is only one zero. We don't see two zeros or two poles at a single location. So there are no multiple poles and zeros for a RC function. Right? How are the poles and zeros? The poles and zeros are all located on the negative real axis. See, this is the real axis sigma. Okay, this part is the positive real part of sigma, and this part on the left hand side is the negative real part of sigma. And where are all the poles and zeros lying? All the poles and zeros are lying on the negative real axis of sigma. Right? This is the second property of RC function. What is the third property? All the poles and zeros are interlaced. What is the meaning of interlaced on the negative axis? Interlaced means they are alternating. So you could see here there is one pole followed by a zero which is followed by a pole which is followed by a zero. Right? So all the poles and zeros are interlaced or they are alternating. There are no consecutive poles, no consecutive zeros appearing. One, if there is a pole, pole is followed by a zero is followed by a pole is again followed by a zero. Right? They are alternating, they are interlaced on the negative real axis. This is the third characteristics of RC function. Now this is the most important characteristics of the RC function. Okay, and what is it? It is the critical frequency. What do you mean by critical frequency? Is that pole and zero which is closer to the origin, right? The poles and zeros are nothing but the frequencies, right? So which is the frequency which is closest to the origin? So for this particular example, which is the one which is closer to origin or on the origin? It's the pole. You could see here, this is the pole. This is the pole which is closest to origin. For this particular example, this pole is on the origin itself, right? So in RC function, it is the pole, it is always the pole which is closest to the origin. Remember, this is a very important characteristics of RC function, that the critical frequency which is closest to the origin is always the pole. Remember, this is a very distinguishing characteristics of an RC function. The pole or the zero which is closest, the one which is closest to origin is always the pole, right, in RC function, and the one which is away from the origin is always the zero. So zero is the one which is far away from the origin. The one which is closer to origin is always the pole. So here for this particular example, the pole is on the origin itself, but it may not be always the case. The critical frequency one is one which is closer to the origin is always the pole. So identify the pole or the zero which is closest to the origin. So if it is the pole, it must be the RC function, right? And the one which is far away must be the zero. And there is never a zero at the origin. In an RC function, there is never a zero at the origin. This is also another very important characteristics of RC function, that there is never a zero at the origin. So let us once again put all the properties of RC function. Recall once again, let us summarize once again the properties of RC function. So what is the first property? All the poles and zeros are lying on the negative real axis, right? All the poles and zeros are on the negative real axis. Further, all the poles and zeros are interlaced. Interlaced means they are one after the other, the pole followed by 0, 0 followed by pole, and so on. There are never repetitive zeros or repetitive poles following one another. Neither there are repetitive poles and repetitive zeros at a particular location. There is only one pole or a single zero at a particular location. And the most important property of RC function is that it is always the pole which is closer to the origin. Zeros are away from the origin, poles are closer to the origin, right? So these are some important characteristics of RC function. With these characteristics, we can easily identify whether the given function is of a RC function or a RL or an LC. On the same lines, let us now discuss RL function. Now let us see what are the characteristics of RL function. So for that, we have been given an example, and a driving point impedance is given to us, and this driving point impedance belongs to RL function. So with this example, let us look at what are the characteristics of RL function. So for that we'll plot the poles and zeros. So let us identify the zeros of the system. So where are we get the zeros of the system by equating the numerator to 0. So equating the numerator to 0, we get the zeros of the system as -1 and -3. So we have obtained the zeros of the system as -1, -3. What are the poles? Poles are obtained by equating the denominator to 0. By equating the denominator to 0, we have obtained the poles as -2, -4. So we have obtained the poles and zeros. Let us plot these pole zeros in the pole 0 plane, in the S plane, pole 0 plot. So we'll plot the first 0. The first 0 is at -1. So you could see here, this is the first 0. The second 0 is at -3. So this is the second 0 which is plotted. The first pole is at -2. So here is your first pole at -2, and the next pole is at -4. So here is your next pole at -4. So we have plotted the poles and zeros in the S plane. Now what do we observe? Now with this pole zero plot, we will analyze the RL functions. Right? What are the characteristics of these RL functions? So first characteristic that we observe is that these poles and zeros are simple. They are not complex, they are simple. There are no multiple poles and zeros, right? At a particular location, there is only one zero or single pole. There are neither multiple poles, neither multiple zeros at a single location. All the poles and zeros are located on the negative real axis. You could see here, all the poles and zeros are located on the negative real axis. The poles and zeros interlace each other, right? It means that 0 is followed by a pole is followed by a 0 is again followed by pole. So they are interlacing, they are alternating each other. And the most important characteristics is again the fourth one, wherein we find the critical frequency which is closest to the origin. What do we identify here? We observe that the pole or the zero which is closest to the origin is always the zero. In an RL function, it is always the zero which is closest to the origin. And what we observed in RC function, it is always the pole which is closer to the origin. But the RL function differs with respect to RC is with respect to this property. Rest all the properties are very similar to RC, but the distinguishing character or the function or the property is the fourth property, which says that the closest pole or the zero, the one which is closest to the origin is always the zero. It is the zero which is closest to the origin, and with this we can identify that this particular function is a RL function. So in RL function, always it is the zero which is closest to the origin, and always the poles are far from the origin. Closest one is always a zero. There is never a pole at origin, right? So at origin you will never have a pole in case of RL functions. So these are the characteristics of RL functions. Now let us look at the characteristics of RC or LC function. We understood RC, we understood RL. Now let us understand the characteristics of LC function. So here is an example of LC function given to us. A driving point impedance of an LC function is given as shown here. Let us identify the poles and zeros from the given impedance driving function. So how do we identify the zeros of the system? We identify the zeros of the system by equating the numerator to 0. So when I equate the numerator to 0, so what is my numerator here? S square plus 1 is 0, or s square plus 9 is 0, right? From these two I get my zeros. So how do I simplify this particular term? So s square plus 1 can be written as s square plus j square. Is it not? We can write s square plus 1 as s square plus j square. J square is nothing but a minus 1, right? J square is nothing but a minus 1. So how we can write it as s square minus j square. So j square is minus 1, minus minus becomes plus, and we get s square plus 1, which is nothing but what was there in the original equation. So s square plus 1 can be written as s square minus j square, and this we can further write it as, we can further express this as s plus j and s minus j. So here we get the zeros from this. If we equate this to 0, what are my zeros? I get my zeros as plus minus j. Right? I get my zeros to be plus minus j as shown here. Similarly, what is my second set of zeros? My second set of zeros is obtained by equating the second term to 0. Right? So s square plus 9 can be written as s square minus 3j square. I can write it as s square minus 3j square. So squaring 3j square is nothing but 9 minus 9. So minus 9 with a minus sign outside becomes plus 9, which is nothing but the original term. Right? What are the terms which I get this? Now if we equate this to 0, we get the two terms. We can write this using a property as a square minus b square as a minus b and a plus b. So I get it as s minus 3j, s plus 3j, and if I now equate this to zeros, what are the values we get? We get two values plus minus 3j. So one value of s is 3j, another value of s is minus 3j, giving me two terms plus minus 3j, which is the second zero. So this is the way you equate the numerator and get the zeros of your system. Similarly, equating the denominator to 0, we get the poles of the system. What we need to now do is plot these poles and zeros. So here is the plotting. Let us plot the zeros first. So there are total 4 zeros. We identify that there are total 4 zeros. So where is the first set of 0 at plus minus j? So you could see here, this is my first 0, this is my second 0. So first 0 is at plus j, second 0 is at minus j. This is the imaginary axis, right? So that's why they are lying on the imaginary axis. Where is my second set of 0? Which is at plus minus 3j. So you could see here plus 3j is my first 0, minus 3j is my second 0. So this way we have plotted all the zeros. Look at the poles. The pole is at 0. The first pole we observe is at 0. So this is the pole which is at 0 located here. And second pole is at plus minus 2j. So plus 2j and minus 2j. So these are the set of poles. So this way we have plotted all the poles and zeros of the system. In the pole zero plot, we can summarize what are the properties of LC function. Right? The poles are and zeros are simple. They are lying on the j omega axis. There are no multiple poles and zeros. All the poles and zeros are lying on the j omega axis. Right? So you could see what was there in RL and RC function, friends. In RL and RC, all the poles and zeros were lying on the negative real axis. So this is the big differentiation between RL, RC and LC functions. So in LC function, all the poles and zeros, they lie on the j omega axis. This is how we can differentiate quickly whether the function is a LC function or an RL or a RC function. So if poles and zeros lie on the j omega axis, we can quickly find out that the given function belongs to an LC function. The next important thing is all the poles 0 which lie on the j omega axis are interlaced. They are again alternating. So every pole is followed by a 0, 0 is followed by a pole. They are alternating. They are interlaced. All the poles and zeros are interlaced. Right? The imaginary poles and zeros occur in complex conjugate pairs. So you could see here each and every pole or a zero, they are appearing in a complex conjugate pole. So if there is a pole at 3j, there is also a pole at minus 3j. If there is a 0 at 2j, at j, there is also a 0 at minus j. Right? So all these poles and zeros are appearing in a complex conjugate pair. Another important characteristics of LC function is that the highest and the lowest power of the numerator or the denominator differs by 1. Right? So for that you can look at the transfer function of our given system. Right, what is the highest power here? When we simplify, the highest power of the numerator is 4. When we simplify the denominator, the highest power of the denominator is 3. So even from the given transfer function, if we look at the power of the numerator and denominator, the always for a LC function, the numerator and the denominator power differs by 1. In a LC function, the numerator and denominator power always differs by 1. And the last property says that there must be a pole or a zero either at origin or at there must be a pole or a zero at origin and infinity. So always there must be either a pole or a zero at the origin. You'll all for an LC function, you'll always see either a pole or a zero at infinity. So if there is a pole at origin, there must be a zero at infinity. If there is a zero at the origin, there must be a pole at infinity. So you'll always observe either a pole or a zero at the origin for an LC function. So the characteristics that we studied, friends, for RL, RC and LC, all these characteristics are going to help us to identify whether the function is a RL function, LC function or a RC function. Okay, so with these properties, now let us try to solve a problem wherein the problem statement is to find out whether the given function belongs to RL, RC or LC. This is very important step before we start to synthesize the given functions. From the given transfer function, by looking at the transfer function and analyzing it, we must be able to identify the elements for which the transfer function is defined. So for the first example, this is the given driving point impedance function given for a particular network. With this example, looking at this particular equation, we must be able to identify whether it defines RL, whether it defines RC or whether it defines LC. So how do we start to identify or to analyze the given transfer function is by starting with the analysis of poles and zeros of the system. So identify the pole and the zero of the system. So what are the poles? The poles of the system are -2 and -6. Denominator equating the denominator to 0. I identify the poles as -2 and -6. Now let us equate the denominator to numerator to 0. By equating the numerator to 0, what do we observe? We observe that the given poles of the by equating the numerator to 0, the zeros of the system are -1 and -3. So we have identified the poles, we have identified the zeros. Let us do the pole zero plot. So here is the pole zero plot. So the 0 is located at -1, the 0 is located at -3, the pole is located at -2 and the last pole is located at -6. So we have done the pole zero plot. With this pole zero plot and the properties that we just discussed, we can identify whether this function is of RL, RC or it belongs to a LC function. Right. So for that, the very first thing that we observe is that all the poles and zeros are lying on the negative x-axis. This is the first observation. The next observation is that all the poles and zeros are interlaced. After the 0 there is a pole, after a pole there is a 0. So all the poles and zeros are interlaced. And the third important property that we look at is who is closer to the origin, whether it is a pole which is closer to the origin or whether it is a 0 which is closer to the origin. So for the given transfer function, we identify that it is the 0 which is closer to the origin. So this is the analysis that you need to do. Now with this analysis, we decide whether it is RL, RC or LC. What we discuss is that if the poles and zeros are on the negative x-axis, then it belongs to either RL or RC. This particular function does not fit for LC because For LC, the poles and zeros must lie on the j omega axis. But what do we observe here, friends? We observe that all the poles and zeros are on the negative real axis, right? And therefore this function must either belong to RL or RC. It cannot belong to LC. Now, whether it is RL or RC is decided by who is closer to the origin. If it is the 0 which is closer to the origin, it is the RL function. If it is the pole which is closer to the origin, then it must be RC. But for the given example, it is the 0 which is closer to the origin, and therefore we say that this is a RL function. The given system is belonging to a RL function. Once we identify this, we can now synthesize the given function. So this particular analysis is very important in deciding the elements from the given function, right? So this particular function is belonging to a. Is the first problem clear? So as the 0 is closer to the origin, as discussed from the previous properties, it is a RL function. Moving to the next example. Here's the second example. This is the transfer function. Driving point impedance given, and we have been asked to find whether this particular driving point impedance belongs to RL, RC, or whether it belongs to LC. To analyze that, we need to first of all identify the zeros and poles of the system. So we'll equate the numerator to 0. That gives us zeros of the system, which are -1 and -3. So zeros of the system are -1 and -3. Let us equate the denominator to 0. By equating the denominator to 0, we get the poles of the system. The poles of the system are 0, -2 and -1. These are the zeros these are the poles of the system. Once we get the zeros and poles of the system, let us plot it. So here we have plotted the poles and zeros of the system. So the first 0 is at -1. The second 0 is at -3. The third, the next pole is at origin 0. The second pole is at -2 and the third pole is at -4. Right? So we have plotted all the poles and zeros. What we observe? We observe that all the poles and zeros are on the negative real axis. They are all interlaced. And the third very important thing is the one which is the pole or the zero, the one which is closer to origin in this case is the pole. The pole is the one which is closer to origin, right? With this, we'll now identify whether this function belongs to RL, RC or LC. Right? What we know, if the poles and zeros are on the negative real axis, they either belong to RL or they belong to RC. This function does not belong to LC because for LC the poles and zeros must lie on the j omega axis. But in this case, the poles and zeros are lying on the negative real axis. Therefore, either this function belongs to RL or to RC. Now, to identify whether it is RL or RC, look at who is closer to the origin. So here it is the pole which is closer to the origin. So if it is the pole which is closer to the origin, it must be an RC function. So we have identified that that this particular function is an RC function by looking at the critical frequency which is closer to the origin. So the critical frequency which is closer to the origin is the pole, and therefore we say that the given function is a RC function. Moving ahead with the example, here is the next example given. We have been given a transfer function, a driving point impedance function, and we have been asked to find whether it belongs to RL, RC or LC. So let us simplify. We have simplified this by taking S common from the numerator and simplifying the denominator factors. So factorizing the denominator, we have obtained the terms as shown here. Now we will identify the poles and zeros of the system. So equating the numerator to 0, we get the poles of the system, we get the zeros of the system. So what are the zeros of the system? The zeros of the system are 0 and plus minus 2j. Similarly, equating the denominator to 0, we obtain the poles of the system. So what are the poles of the system? The poles of the system are plus minus 3j and plus minus 2j. So these are the poles of the system. So equating the numerator, we obtain the zeros, and equating the denominator, we have obtained the poles. Now we'll plot the poles and zeros. So 0, the first 0 is at plus minus 2j. You could see here at 2j and minus 2j we have plotted the 0. There is another 0 at origin. You could see here there is one 0 at origin. We will now plot the poles. The first pole is at plus minus j. So here you could see at j and minus j we have plotted the poles. Another pole is at plus minus 3j. So one pole is at 3j, another pole is at minus 3j. So what do we observe from the pole 0 plot? We observe that all the poles and zeros are located on the j omega axis, on the imaginary axis. All the poles and zeros are located on the j omega axis. All of them are interlaced. 0 followed by pole, pole followed by 0. All of them are interlaced. And the one more important thing we observe is that in the given transfer function, right, the difference in the order of numerator and denominator is by 1. The highest order of the numerator is 3. Highest order in the denominator is 4. So they differ by 1. All these characteristics are of LC function. The moment we see poles and zeros on the j omega axis, we can conclude that it is LC function, because for RL and RC, the poles and zeros must be on the negative real axis, right? But if the poles are on the j omega axis, we can definitely conclude that the given function is for an LC function. So this way we can, with the properties of RL, RC and properties of LC, we can quickly identify whether the function belongs to RC, RL or LC.